Good evening, students. Today we are going to discuss the important topic in graph theory, that is graph isomorphism. So what is isomorphism in graph theory and how to identify whether two graphs are isomorphic or not? If we are going to take this subject, we always consider two graphs for considerations. So when we take two graphs only, we can check whether it is isomorphic or not. So with take off one graph, we can't say is it isomorphic or not. So we always consider two graphs. So when we say two graphs are isomorphic or not, so there is some definitions. So first basic thing, maximum they ask about isomorphic means trivially same, whether isomorphic or not isomorphic, trivially they have same number of vertices and the same number of edges. So there is no issues in number of vertices and the number of edges. Right? The main point is exist a one-to-one correspondence between the graph. What mean by one-to-one correspondence? Right? We are going to check what mean by one-to-one correspondence between the graph. Right? That is the important condition for check both graphs are isomorphic or not. So what is the first condition? Same number of vertices. Second condition, same number of edges. Third one may be given equal degree also, right? So with this help of three conditions, we can't say it is isomorphic. The last one, right, that is called one-to-one correspondence. So let us example for consider whether it is isomorphic or not. So in this diagram, how many vertices are there? Yes, of course, the same number of vertices, 5 vertices, here also 5 vertices. How many edges? 1, 2, 3, 4 edges and 5, 6 edges. Here also 1, 2, 3, 4, 5, 6 edges. Yeah, edges also equal. What about degree of the vertices? Degree 2. How many degree 2 vertices in a graph G? How many degree 2 vertices? 1, 2. What mean by degree? Number of edges incident with that vertex is called degree. Degree 2, right? Degree 3. And degree of this vertex 2, degree of this vertex 3, degree of this vertex 2. So 3 vertex have degree 2, 2 vertex have degree 3. The same scenario should be in graph G dash, right? If it is isomorphic. So check it, degree 2, 3, right? Degree 2, degree 2, so degree 3 and degree 2. The same here also, 2 degree vertices, right, and degree 3 degree vertices is number 2. So degree sequence also same, degree sequence also same, right. Now by using this condition we can say isomorphic. Check well, right, in G, how many vertices have adjacent with other vertices? Let us consider my word, so important to check whether it is isomorphic or not. This vertex have degree 2. Adjacent with a vertex, that vertex have degree 3. Another vertex also have degree 3. Another, these 2 degree vertex adjacent with degree 3 vertex only. Degree 2 vertex adjacent only, degree 3 vertex. The same scenario should be in second graph, right? Check it now. Degree 2 adjacent with 3. Degree 2 adjacent with 3, degree 2 adjacent with 3. That's why trivially say it is isomorphic graph, right? So we can map the vertices from G to G dash. So it is no more important, but anyhow, final answer we could map all the elements. So here if you take U1, right, if you take U1 in the graph G, and instead of U1, 2 degree mapping to V1. Instead of U4, maybe mapping to V3. Instead of U2, 3 degree vertices mapping to another 3 degree vertices. These 3 degree vertices also mapping here. These 2 degree vertices also mapping here. So simply mapping. Mapping may not be unique, right? Different mapping may be accepted, right? But mapping should be have 2 vertices degree to 2 vertices degree, 3 vertices degree to 3 degree vertices only, right? So this graph is simply one-to-one correspondence between the graph. So directly we are going to say It is isomorphic. So when we discuss about not isomorphic means easily we can understand the concept of isomorphic. So come to the next problem. So if simply look, it may be treated as isomorphic, but check well. After checking the condition, it is not isomorphic. Okay, so if you understand very well, you can solve any problem regarding isomorphic. Okay, so now come to the problems. Two graphs are given. If you can't see the vertices, no issue. Simply we can understand the concept, right? In a graph G, and consider the graph G dash. Check the number of vertices. 4 vertices. Inside of the box also 4 vertices, 8 vertices. Here also 4 plus 4, 8 vertices, right? Number of edges, 1, 2, 3, 4, 5, 6, 7, 8, and this black line also 1 edges, 9 and 10 edges in graph G. Check it graph G dash, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges in G dash. So no issue about edges also, right? After the degree sequence, how many degree vertices have degree 2? 1 vertices, 2 vertices, 3 vertices, 4 vertices. Here, how many vertices have degree 2? 1, 2, 3, 4. Once again repeated, what mean by degree? Number of edges incident on that vertex. How many vertices have degree 3? 1. Degree 3 vertex, it is 1. Another one, 2. Right? Here also degree 3 and here also degree 3. So 4 vertices have degree 3. Here check it, 1, 2, 3, 4 vertices have degree 3. Sir, everything is right, sir. Then what about the issues? Why we can't directly write isomorphic? Now come to the conclusion. Clearly understand this conclusion for understanding the entire concept in isomorphic, right? Here degree 2 vertex adjacent with a vertex have degree 3 only. Degree 2 vertex adjacent with a vertex have degree 3. Degree 2 vertex adjacent with a vertex have degree 3. Degree 2 vertex adjacent with a vertex have degree 3. So what about G? Understand my word? All the vertex have degree 2, only adjacent with a vertex have degree 3. So check it now in G dash. A vertex have degree 2, also adjacent with a vertex have degree 2 only. Right? Here also a vertex have degree 2, adjacent with a vertex have 2 only. So this degree sequence is not mapping, is not similar to G dash and G. That's why it is not isomorphic. We can't mapping the vertices also, right? So if I mapping these vertices to, this means, right? But this vertex have degree 3. This vertex also degree 3. But here the adjacent vertices have degree 2 only. So we can't map. That's why it is not isomorphic. Okay? So with help of that reason, we can say which is not true, therefore it is not isomorphic. Come to the third one, the same, right? 3 plus 2, 5 vertices, 5 vertices. 1, 2, 3, 4, 5, 6 edges, 6 edges. Then what about here? Directly we can say, right? Simply watch, we can understand, right? Here there is available pendant vertex. What mean by pendant vertex? Degree of this vertex is 1. Here there is no pendant vertex. There is no degree 1 vertex. Simply we can say degree sequence is not match. So it is not isomorphic. Even number of vertices, number of edges are same, but degree sequence itself not right. So it is also not isomorphic. Come to the next one. Yeah, good, excellent problem, right? 3, 4, 5, 6 vertices, 6 vertices, 3, 4, 5 edges, 5 edges, right? Degree 1, 1, 2, 3 vertices, 1, 2, 3 vertices have degree 1. Degree 2, 1, 2, here also 1, 2. Degree 3, 1 vertices, 1 vertices. Sir, all are same, sir. Why can't we directly say isomorphic? Yes, very excellent problem to discuss about isomorphic or not isomorphic. Come to the conclusion. Here, two vertex have degree 1 adjacent with a vertex have degree 3. Right? Here, how many vertex adjacent with degree 3? This only one vertex have adjacent with degree 3. Right? How many vertex are adjacent with degree 3 vertex? Only one pendant vertex. What mean by pendant vertex? Degree is 1. That is called one pendant vertex only adjacent with degree 3. But here two pendant vertex are adjacent with the vertex have degree 3. That's why it is also not isomorphic. Right? So not isomorphic. Yes, of course, if you say check all the things, it will be isomorphic. Check it. Okay. And yeah, another interesting one. So when you simply say it may be not isomorphic in your point of view, but after complete it is the isomorphic only. Why? 4 plus 4 8 vertex. Here also 8 vertex. Edges 4 plus 4 8 9 10 11 12 edges. Here also 12 edges. Yes, all the vertex have degree 2. Adjacent with the vertex have degree 3. Sorry, degree 3. Adjacent with, sorry to say, degree 3. Adjacent with degree 3. Degree 3 adjacent with degree 3. Right? 3 adjacent with 3 only. There is no degree 2 vertex. Yes, the same scenario only here also. Right? Degree 3. It is not a vertex. Mind it, it is not a vertex. It is not a vertex, right? It is the simple intersection point only, right? So don't consider it is a vertex. So how many vertex? 1, 2, 3, 4, 5, 6, 7, 8 vertex. Yes, count it. It is considered as 1 edge and 2 edge, right? 3 edge, 4 edge, 5, 6, 7, 8, right? So all the edges are same and all the vertex have degree 3 adjacent with degree 3 only. Degree 3 adjacent with degree 3 only, right? So it is also isomorphic, not isomorphic. Don't say yes, not isomorphic. It is absolutely isomorphic graph, right? Once again, repeat the video, you can check whether it is isomorphic or not. Yes, of course, it is a simple thing. We can check whether it is isomorphic. Construct the adjacency matrix. What mean by adjacency matrix? From this graph, if connected U1 to U1, there is no loop for U1 to U1, right? That's why it becomes 0. If it is connected 1, not connected 0. U1 to U2 connected, right? U1 to U3 connected 1. U1 to U4 connected 1. U2 to U1 connected, right? In G. U2 to U2 there is no loop. U2 to U3 connected, U2 to U3 connected, right? So you should put 1, right? You should put 1. U2 to U4 connected 1, right? So I sorry to say it is 1, right? U3 to U4 connected, U3 to U1 connected, right? And U3 to U2 not connected, that's why 0, right? So first construct the adjacency matrix for G1 or G and then adjacency matrix of G2. How to check? From this given matrix G, you should get the matrix G dash, adjacency matrix of second graph. By interchange, you can interchange the rows or interchange the column. Fully interchange, right? Not to a single element. If you want to interchange third column and fourth column means simply interchange all the elements from third column into fourth column and all the elements come from fourth column into third column. So similar way, if I check, right, what is the first one? Third column convert into fourth column, right? Where it is, check again, right? This third column 1001, right, convert into fourth column. This fourth column convert into third column. That is the resultant matrix. After that, I want to get this matrix. It should be a final matrix. If I get, it is isomorphic. Yes. After that, third row. What is the third row? 1 0 1 0. Right. This third row comes to which one comes to fourth row, I think, right? Third row comes to fourth row and the fourth row comes to third row, right? 1101. So yes, of course, we get a adjacency matrix of G dash, right? Whatever may be is given, right? Try to get from first matrix to second matrix by interchange row and column, then we can say isomorphic. If not get a second matrix from the first matrix, then it is not isomorphic, right? So already important theorems we discussed in the last class. So it is the concept main in isomorphic. So please listen, whatever problem is given in the isomorphic, easily can get full mark in isomorphic because it's look like a optionable question only, right? There are only three options, whether it is isomorphic or not isomorphic means it's a lot of options, but here only one single option. If you say isomorphic, answer is right, get full mark, right? Proper conditions, proper requirements are applicable. Okay, thank you. I hope you understand this class. Thank you very much. Okay.